Okay, so the previous bonus video was focusing on what Arnold was doing on the previous lecture, essentially, and this one is now focusing on kind of preview of what he was doing on the week 7 lecture. And he started to use shear flow, but for more complicated shapes. So no longer looking at T-beams and I-beams, but what's more complicated than that? But a box. So let's look at this equation, because this is something that's going to become relevant here. So we've got the shear flow times by the spacing between our bolts there, and they've got to be less than an acceptable applied force that a particular bolt can take. Now let's consider, do I want to discard? Probably not. A box, and we'll look at two types of boxes we could have. We'd have a box where we're taking our plates and put them together this way around. Or we could have a box where we have a large upper plate. And so the way that my bolts are going to be applied for this one will be going across like this. And for this one, from above and below. So how do we use the equation of our shear flow in this particular case? So we know the V, that's fine. That's going to come from maybe the question, from our calculations for the bending moment of the beam, whatever. Cross section of I, that's fine, we know that. But what about the Q? So this is, and I suppose also the T. What are we going to do for that? And also the fact that I'm now dealing with a box. So starting point for this is, how do we define the Q, the big Q, for these problems? So you've got to identify a section which is going to have the slicing action between one part of the body and the other part of the body. Which part of the body you accept is going to be the part of the body of interest is kind of irrelevant. But typically you would use the smaller area. Let's try and use so this one here. It would make sense to isolate that as a section of body where we can imagine this section of the body trying to shear away from the rest of the body, and it would make sense to select this section of the body trying to shear away. Okay, because this one looks more like a kind of traditional problem where we've got an upper sort of Y value away from the neutral axis, so that all looks fairly standard. This one here, of course, we've now got shearing not in the plane that we're used to, so we're not no longer got a horizontal shear, but we've got a vertical shear. How do we deal with that? Before I talk about that, I suppose I should mention, as we're looking at bolt problems, the QS less than the force that the bolt can be subject to, you now need to count number of bolts. and need to put that into your equation. So that's basically the more bolts that you're trying to shear across, that's going to reduce this particular value here. So you can divide this by n. So here we've got a section. It's shearing through 2 bolts. So the condition that we're looking for is that the little q, the spacing as I'm looking down the beam between my bolts. In this case, they're in the side. The spacing there is the little q, the spacing, and the number of bolts that's involved in my identified section that's being sheared, which is going to be 2, is going to be less than some defined force. Okay. Similar thing here. We're shearing through 2 bolts. With our I problem, obviously we were just shearing through 1 bolt, so n would be 1 there. So that's a point to mention about the number of bolts. Okay. What did I want to talk about next? So the T in this particular case, it's going to be the thickness of the contact if we were gluing these things together. So if we weren't bolting but using glue, then we would be looking at our contact. So in this case, that would be my T, and this would be my T. What else? The other thing is that it's dependent upon, you're assuming that you're taking Lego things and you're sticking them together, and it's only the bits where they're sort of joining together where we're arguing that these things can move. So if I did an object like this, actually I should have made that a bit bigger to emphasize it. So I had an upper plate, and it was stuck onto a lower sort of plate here. We are going to use some glue. What we'd be interested in there would be finding maybe the shear. So we'd be looking at the Q divided by T. So this would be the thickness of the contact, QIT. And the second moment of area that I would be looking for would not be what you might think, this upper section. Okay, we imagine that body is all acting as one, so it's actually the entire. We imagine that the Q here is going to be that entire found from that entire section of that body. So we have to find the Q from this bit, even though it's got overhanging bits which are lower than the distance that you're looking at, that's sort of contact to the body. So that's another point to make. I think that covers it really. So we're now going to get some sort of vertical contacts as well as horizontal contacts. Don't think we see these examples, but I thought I'd mention that just in case, that you're interested in finding the first moment of area of the particular body. You've got to identify a particular body that's trying to shear away from the other part of the body. And if you're dealing with bolts or nails, you need to add up how many bolts or nails and then take that into account. And so divide that basically by that value there. So that should cover everything. The other thing is, not that you'd want to, you could analyze this problem. No reason not to. Well, there is a good reason not to, but you could analyze it by working out what the Q is for the dark green, okay? And you can imagine that the dark green is trying to shear away from the light green, and that would then be the Q that you're looking for. Your T would still be the same, but obviously that doesn't really make sense, because you're having to work out various sections to work out what that Q is. So it's not a brilliant idea. Okay, so I think that covers a lot of the ideas that were covered in his week 7 lecture. Yeah, I think that's all I can think about for now.